Hey, we have another integral today. This one's from MIT 2012, problem number 8. We have the integral from 0 to pi over 2 of dx over 1 plus sine x. I think what I'm going to do here is just take a straightforward method, pretty basic, and try to do this integral, but we're going to run into some trouble later on. So let's get into it and see where we have a problem. To start, all I'm going to do is multiply the top and bottom by the conjugate of 1 plus sine x. We'll multiply by 1 minus sine x. Then multiplying this out, we're going to have 1 minus sine x in the numerator, and then we'll have 1 minus sine squared x in the denominator. But this is just cosine squared x. We can write it that way. And then what I'll do is, let's just divide it into the numerators so that when we do that, 1 over cosine squared x, we're going to have a secant squared x. And then sine over cosine squared x, we can write that as tan x times secant x dx. And the good thing about that is each of these are well-known common integrals, so we can just integrate real quick. Integral of secant squared x is going to be just tan x. Integral of tan times secant is just going to be secant x. So we have a very quick and easy integral evaluated from 0 to pi over 2. Next, we'll try to evaluate this, and we have tan at pi over 2, okay, minus secant pi over 2. And before we go any further, tan of pi over 2 is heading towards infinity, and secant of pi over 2 is also heading to infinity. So we have this kind of, and so when we evaluate and we get infinities, we kind of have a problem. So let's look at this a different way. One thing I can do here is I can break this into sines and cosines. So we can write tan pi over 2 as sine pi over 2 over cosine pi over 2. And then for our secant, we can write it as 1 over cosine pi over 2. And we have the same denominator, so this is sine pi over 2 minus 1 over cosine pi over 2. Then sine of pi over 2 is just 1, and cosine pi over 2 is 0. 1 minus 1 is 0. Cosine of pi over 2, we end up with 0 over 0. And so again, at this point, we're stuck. We're kind of stuck. This is an indeterminate form here, but what that allows us to do is then, in this case, we can use L'Hopital's rule. Okay, real briefly on L'Hopital's rule, over here to the right, we have this definition. Now, we only can use this for an indeterminate form. Like we saw, we had 0 over 0. This would also work for infinity over infinity situations, but we need that indeterminate form in order to use this with some restrictions. And it just tells us that if we have a limit of f(x) over g of x, in that case, we can evaluate the limit at the derivative of the numerator and the denominator, our f of x and g of x. So specifically, I've written this in this form. I've written our tan x minus secant x as sine x minus 1 over cosine x. Then to use L'Hopital's rule, we want to evaluate this sine x minus 1 over cosine x over here. But we're just evaluating, we're not interested in the 0 part right now, we're just interested in evaluating the limit at pi over 2. And previously we determined this was 0 over 0, so this was our indeterminate form. So that's going to allow us to use this over here, and we'll look at the limit as x approaches pi over 2. The derivative of our numerator is going to be just cosine of x with derivative of 1, 0. Derivative of cosine x is going to be minus sine x. Now when we evaluate this, we look at pi over 2, cosine of pi over 2, that's heading towards 0. Then the limit of sine x at pi over 2 is going to be just 1. You have that minus sign, but it's not going to matter because 0 over minus 1 is just 0. Therefore, evaluating this at pi over 2, we're just going to have this 0. And with L'Hopital's rule, that's how we can get around that 0 over 0 situation. Okay, now we just need to evaluate the second part. We need to evaluate this at 0. So plugging a 0 in for sine, we're going to have 0. So we're going to have a minus 1. And then cosine at 0 is just 1. So then just to finish it off, we're going to have 0 minus minus 1. These cancel. And for our answer, we're just going to have 1. That's it. Thought it was a pretty interesting problem from MIT 2012. Thanks everyone for watching. Have a good day.